And the third equation of heat exchangers is the overall heat transfer coefficient. We have this tube in the heat exchanger, right? Let's say for now that we have hot fluid here. Let's say we have cold fluid here. So let's start building. As the heat goes out of the inside fluid to the outside fluid, right? It has to overcome a series of resistances, thermal resistances. Number one, are these series thermal resistances or parallel thermal resistances? Somebody said series. Who was it? You? Okay, thank you. It's exactly true. I mean, if you have radiation, there might be some subtlety. Let's forget about that. So at least we have three resistances here. I'm going to make them on this other side. I have resistance to conduction, right? Then I'm going to have, actually, don't draw anything yet. Don't draw anything yet. Please, I'm going to modify this soon. Two other resistances we have for sure. Which would those be? Convection. So let's say we have resistance to convection of the cold fluid here, resistance to convection of the cold fluid here. Now look how it all is coming together. Crazy stuff. For sorry, this is a hot, right? For the hot, you need to use what we have learned in the internal flows class. For the cold, you have to use what we learned in the external flows week, right? For conduction, you need to use what we learned in the conduction classes. It all comes together. So in reality, heat exchangers, other than this fudge factor, is just everything we have learned so far all together for you. All right, but I ask you not to do that, that drawing yet. And the reason is, right, here we have, this would be T of the hot fluid, T of the cold fluid. Let's say that we have what always happens here in this province. You have all these asphaltenes and all these things that you chemists love, right? And they deposit in here. Right? You know what that's called? Fouling. Fouling. Right? So, and just for the sake of example, let's say we have fouling outside. Why not? Right. The reason I didn't want you to draw this yet is, where do those resistances go?
On either side of the conduction.
Exactly right. We'll go here. Right, so here we would have foul on the cold side, on the hot side. In addition of having the fouling, we could have finned tubes, right? And for finned tubes, we saw these formulas when we were looking at the heat transfer mechanisms. We talked about when we were looking at thermal resistances. So we saw these formulas. So now if I write the formula for overall heat exchange heat transfer coefficient, we have about the fouling I wanted to show you. There are tables for fouling. And this interesting thing about fouling is that fouling increases with time. So if you have the rate of, this is super late. If you have the rate of growth of fouling then you can predict when you have to service the heat exchanger. So I'm off by 5 minutes. So let's stop here. I'll finish up the equation next class, and I'll see you on Friday. Okay, so now this formula that I gave you for overall heat transfer coefficient, this is very general. This is for tubes that can have fouling and fins, whatnot, right? It has the works. You can calculate anything you want with that. Did I have something on fouling? I had a slide on fouling here, right? And fouling typically is tabulated. What you see there in the book, right, is kind of half true and half not. The reason is when the heat exchanger is new, fouling is 0, of course. And with time, fouling increases. So the really interesting thing is when you have the progression of fouling with time, right? Because then you are able to anticipate the performance of your heat exchanger, and you can design for preventative maintenance, for shutdowns. You can do it as part of your design from the beginning, saying, okay, how long do I need? Can I run it before I need to shut it down, or how big should it be to be able to run for 1 year without the performance we want? So all these things that look just like ink on the board, all these things actually are quite powerful. Quite powerful.